Hello there to all my distance learning Calc 1 students. So this is our first video of distance learning, and in this video I'll wrap up section 5.5. As I said when we first covered this, when you're dealing with definite integrals and u substitutions, there's a subtlety involved with that that I've learned actually means I need a separate class day on it, which is fine, and that's what we'll do today. So today we'll handle definite integrals in contrast to indefinite integrals, which we did last time. In particular, there's a common error that should be avoided, and also we'll just do some more practice with u substitutions. That's the point of this. Okay, so let's jump right into it. So for each example, I'm going to show you two separate ways to do it correctly and then point out the way that you do it incorrectly, that is this common error. Okay, so for this example one, here's the first way you could do this problem. So this is option one. The first thing you could do is just make that a little more readable. You could forget about the limits for now, because recall, when you're evaluating a definite integral, there are two steps. The first step is to find an antiderivative, and then after that you can consider those numbers. So let me do that here. So u is x squared, du is 2x dx. So that integral becomes e to the u du. That then becomes e to the u plus c, and then we translate it back, e to the x squared plus c. So there you go. This is just like in class last time, doing indefinite integration using a u substitution. So once you've done that, then you can say to yourself, oh yeah, but there's like a 0 and a 3 right there. I should deal with that, shouldn't I? So now you're moving on to step 2 of using the fundamental theorem of calculus to evaluate an integral. So then you say, okay, well, I pick my favorite antiderivative, and I got a whole family here, right? I pick my favorite antiderivative, and of course our favorite is when c equals 0. And then I say, okay, so therefore integral 0 to 3, 2x e to the x squared is equal to e to the x squared evaluated from 0 to 3. So this is what? E to the 3 squared, so e to the 9th, minus e to the 0 squared. E to the 0 is 1. So there you go. So the area under the curve of 2x e to the x squared from 0 to 3, that area is e to the 9th minus 1. So here's option 1. Here's one way you could deal with bounds on the integral now, definite integral. You can just do exactly what we did last time, and then at the end be like, oh yeah, I can let c be 0 and then do this thing, right? There are my x bounds, and I plug into the antiderivative and subtract. So you could do that. There's a second thing you could do. So here's option 2, like this. So you can do the same kind of thing, only now I'm going to keep the bounds on here, 2x e to the x squared dx. You can still do your u substitution like this. So this is all the same so far. Okay, but now when you write equals here, if you're going to keep the bounds on the integral, when you do this e to the u du part now, this second integral is a u integral. It's not an x integral. Make this u a little better. Okay, so the 0 and 3 right here, these are x bounds in the x language. It's not clear at all, and in fact, usually it won't be true that those numbers carry over. So if you want to do it this way, if you want to keep the bounds from the start, you have to do this. You have to say, okay, when x is 0, what is u? Well, u is x squared, right? So when x is 0, that would mean that u is also 0. Well, so this first 0 right here stays a 0 right there. So when you translate when you translate 0 from x's to u's, you don't change anything. But what about when x is 3? Well, if u is x squared, that would mean that u is 9. So you could put a 9 right there, and then you could just proceed this way, not even bothering translating back to x's. So e to the 9th minus e to the 0, which is 1. You get the same answer, of course, right? So we already knew the answer was e to the 9th minus 1. So all that to say, in the second way of doing things, you can keep the bounds, like I have highlighted still here, right? Keep the bounds 0 and 3. You then have to translate those bounds to u bounds, though. And then you can do the antiderivative in terms of u, not translate back to x's, keep your u bounds there, and you're done. Here are the two ways you can deal with with a definite integration using u substitution. Let me zoom out a little bit. There they are. There are two correct ways to do it. Let me now show you the common mistake. And let me just say, like, no, bad. I'm like so sad if you do this. I'm gonna draw a little. Oh, look at how sad I am. I'm crying. If you do this, I'm going to be sad. So this is wrong. So you can probably anticipate what the mistake is, but let me do it anyway. So you start the same way as option 2. You make your u substitution. And then you do this. You say, okay, the new integral is e to the u, and it's from 0 to 3. So you don't translate the x bounds into u bounds. That is bad, because as we've seen, right, the viewing window didn't stay at 0, 3. We saw that in option 2, right? You couldn't keep the viewing window from 0 to 3. You actually had to expand it in this example to go from 0 to 9. So if you do this, you will, of course, get the wrong answer. So you do e to the u from 0 to 3, and you end up writing that the answer is e cubed minus 1, which, of course, is wrong. We already knew the answer was e to the 9th minus 1. So this is like, you shouldn't do this. But that's a pretty common error to see on exams. So option 1 or option 2 are the way to go. And on an exam, I don't care which one you choose. You should, of course, write the work the way I've written it, right? So notice how beautiful my work is. There are no false statements there. All the notation is correct, right? There's like a dx there, a du there. You have to remember those things. Notice in this chain of work here, all of these equals are true. And these are indefinite integrals here, which is why I need the plus c, so I don't make a false statement. But then you can like sort of forget about the c when you move right there. Okay, so that's how you deal with definite integrals with u substitutions. So let me show you a couple more examples, and then we'll be out of here. Okay, so let's think about this integral here. From 1 to 2 of e to the 1 over x squared over x cubed. So part of the reason we're doing this is to practice more with u substitution. So, again, we have to spot sort of like an interior function whose derivative is there. And you can make some guesses if you want to, as we saw last time, right? If you don't know, you can always make a guess. But the thing is, there's an x to the minus 2 up there in the e, right? There's an inside function right there. And du is negative 2x to the minus 3, otherwise known as negative 2 over x cubed. So that's what du is. Sorry, I forgot my dx here. Okay, and so notice this integral, I could rewrite it like this. Integral from 1 to 2, e to the 1 over x squared times 1 over x cubed. So there's your multiplication of a derivative. Now, as we saw last time, you don't have to hit the derivative on the nose. So the fact that there's a negative 2 in the du part, when you want a 1, is fine. You just have to massage this equation a little bit, and here's how that goes. So divide by negative 2, and now you have your 1 over x cubed dx. Okay, so now I'm going to do option 1 here. I'm going to say, well, integral of e to the 1 over x squared over x cubed, that is indefinite integral. Sorry, I forgot my du there. That is the indefinite integral of e to the u, right? Because u is 1 over x squared. And then the 1 over x cubed dx gets replaced with a negative half du. So let me actually put the negative half front. So negative 1/2 e to the u du. So now I can integrate that. That's negative 1/2, right? The e to the u just goes to itself, plus c. Therefore, the antiderivative is negative 1/2 e to the u, but that's just e to the 1 over x squared plus c. Okay, so therefore, the original integral is take this antiderivative, but set c equal to 0. Evaluate from 1 to 2. So it's going to look a little messy, but it is what it is. So I have negative 1/2 e to the 1/4, it looks like, power. So like a 4th root of e. Now I have to subtract off plugging in 1. Excuse me, plugging in 1. So that'd be a minus a half, right? So there's a minus here already, isn't there? So you got to take that into account. Minus a half, so you get plus 1/2 e to the 1 power, right? 1 over 1 squared. So there's your answer from option 1. Okay, so again, if you want to do option 2, let me show you that. Okay, so the u stuff is all the same, so I don't need to rewrite all that. Like all that would stay the same. And so then you would say integral from 1 to 2 now, keep the limits on there, e to the 1 over x squared times 1 over x cubed dx equals integral, so it's going to be negative a half e to the u du, but the question is, what are the bounds? So when x is 1, what is u? So here's the relevant equation, right? U is 1 over x squared. Well, x to the 1 to the negative 2 power is still 1. So that stays the same. Let's think about when x is 2, what is u? When x is 2, what is u? U is 1/4. So there's a 1/4 right there. And sorry, my 4 looks like a u. Let me make that maybe a little better. 1 over 4, like that. Okay, so off we go. This is negative 1/2 e to the u, evaluated from 1 to 1/4. It's kind of weird to have the bigger number on the bottom, but you can just take it as it is. 1/4, like that. Okay, so let's plug in and see what we get. We get negative 1/2 e to the 1/4. The top number always gets plugged in first. And then you got to subtract off, plugging in 1, but subtract the half, right? You then get a plus 1/2 e, and that checks out, right? Because it agrees with our previous one. Okay, so again, for this one,